So we've looked at the first derivative to see how it tells us about stationary points and critical points and whether a function is increasing or decreasing. Now let's look at the second derivative, so it'll tell us a little bit about the shape of our function. First, we say that a graph is concave up at x equal a if f prime is increasing at x equal a. And then likewise, concave down if f prime is decreasing. So what does that mean? Well, everything we do we can relate back to what we know between a function and its derivative. So when we're talking about f prime increasing, that means the derivative of f prime is positive. That would make f prime increasing. And if the derivative of f prime is negative, then f prime is decreasing. Any point where a graph's direction of concavity changes, we call that an inflection point. And we have two types of inflection points that we should be familiar with. Grab my arrow and bring that down in case I need it. So if the tangent line is horizontal at an inflection point, the point is called a stationary inflection point. Otherwise, it's called, no surprise, a non-stationary inflection point. So let me give you an example with just a simple picture here. Let's say we have, let's go with, a red graph. Let's say we have the graph of like y equals x cubed. At 0, this is y equals x cubed. So the first derivative is equal to 3x squared. And so at x equals 0, y prime is equal to 0, which means that we have a stationary point and the tangent line drawn there is horizontal. On the other hand, let's say that we have, let's draw a different graph. Say we have something like that. Now, at this point here, our tangent line, draw that in a different color. There's our tangent line. So at that point, our graph is changing concavity from concave down to concave up. So we have an inflection point there, but the tangent line is not horizontal. And if we're looking at the slopes of the tangent lines at that inflection point, notice that, here we have a 0 slope, so we have a maximum of our function f, and I should have labeled these, this is f. And then we have a negative slope tangent line, and then more negative, more negative. Finally, we have most negative, and then less negative, less negative, less negative, and then 0 again. So notice at that inflection point, the slope of our tangent line was most negative, which means the graph of f prime will have a minimum there. And so the derivative of that f prime graph will have, the tangent line will be a slope of 0. So an inflection point, in my green example, the inflection point is an extremum of f prime, which means it's a 0 of f double prime. So those are the two types of inflection points. We have stationary inflection, and for both of these, f double prime is 0. But if f prime is also 0, then it's a stationary inflection point. Otherwise, non-stationary inflection point. Let's look at an example and make sure that we can tie all this together. So here's a function. We have a quartic polynomial. We want to find and classify all the points where the derivative is 0. And then we want to classify all the inflection points. Find intervals where our function's increasing and decreasing. Find intervals where it's concave up, concave down, and then draw a quick sketch of that function. So let's try and put all this together. So first let's look at f prime. And f prime is going to be 12x cubed minus 48x squared plus 48x minus 0. And we want to set this equal to 0. We can factor out a 12x. And we're left with an x squared minus 4x plus 4. So that's going to give me an x minus 2 times x minus 2. So we have roots of 0 and 2. The root at 2 has a multiplicity of 2. So let's make a sign chart for this. And we'll have our x value here and our f prime value here. And our stationary points, our critical points, are when x is 0 and when x is 2. And we know our derivative is 0 at those 2 points. So let's figure out, lost my blue arrow. Let's figure out in the intervals between those and see if our derivative is positive or negative. And we'll fill that in. So, my pencil, there we go. All right, so let's pick a number like -1. When I plug in -1, I'm going to get a negative and a negative and a negative. Multiplied together gives me a negative. Let's try a number like +1, something between 0 and 2. Plug in 1, we get a positive times a negative times a negative. That's going to be a positive. And then let's try something bigger than 2, like 3. Positive, positive, positive. So once again, this is a classic example where you don't just figure out one of these intervals and then alternate signs. And that's because we had the double root there. All right, so what does this tell us? This tells me that my function f is decreasing from -infinity to 0. Then it's increasing from 0 to 2, levels off instantaneously, and then it increases more. So we would actually say it's increasing from 0 to infinity. All right, so now we've answered, let's go ahead and fill that in. So increasing from 0 to infinity. In IB's terms, they would include the 0, so they would put a bracket like that. And then not including is a reverse bracket. And then decreasing from -infinity to 0. I think it makes more sense not to include the endpoints, even though IB does like to include the endpoints. All right, so what else can we do? We've got find and classify where the derivative is 0. So I'm going to come back and answer A after I do the second derivative. So let's do f double prime. And we're going to get 36x squared minus 96x plus 48. Alright, so now we want to set this equal to 0. What goes into all of those? Let's see. 2 times 18, 96 is 12 times 9. 12 goes into everything. We factor out a 12. We're left with 3x squared minus 8x plus 4. And can we factor that? X and x, we break the 4 down to a 2 and 2, make them both negative. That gives me a -2x, a -6x is a -8x, and a plus 4. Check. So we get zeros at 2, which we already knew. So that's telling us that we have a stationary inflection point at 2. And then we also have at positive 2/3. So once again, let's make our sign chart. And let's include those. So we've got when x is positive 2/3 and when x equals 2. Now we're looking at the second derivative. And the second derivative is 0 at those 2 points. And now let's figure out our concavity. So let's pick a number smaller than 2/3, like 0, and we get a positive 48. If we pick a number between 2/3 and 2, like 1, we're going to get a positive times a negative. And pick a number bigger than 2, like 3, and we'll get all positives multiplied together, gives us all positives. So, let's slide this up just a bit for a second here. So what does that tell us? It tells us if f double prime is positive, 0, and negative, so we have concave up, concave down, concave up again. Alright, so let's go ahead and fill in. And by the way, since the second derivative is 0, these are inflection points at 2/3 and 2. Since the first derivative at 2 is also 0, then when x is 2, we have a stationary inflection point. Now we'll go ahead and continue answering these. So x equals 0 is a stationary point, and it's also, if our function is decreasing, let me point to this. If f prime is negative, we know our f is decreasing, then it levels off, and then it's increasing. So that tells us it's decreasing, levels off, increasing. Tells us that we have a local minimum. And then at x equal 2, we have a stationary inflection point. So it's changing concavity at that point. So I've already answered B, find and classify all points of inflection. So we've already got the x equal 2, leave that there, stationary inflection point. And then at x equals 2/3, we have a non-stationary inflection point. All right, find the intervals where it's concave up, concave down. So concave up from our green sign chart. We know it's concave up from -infinity to 2/3. Once again, I don't include the endpoints. IB likes to include them. And then also from 2 to infinity. And then it's concave down from 2/3 to 2. Sketch the function from the above information. So we could go ahead and draw a rough sketch. I can just go ahead and put it, I already graphed it on the calculator. We've got y equal. So there you see that, let me trace it at 2/3. So at 0 we have a local minimum, 0, -9. And I should probably put the y values in here for us. So 0, -9 is our local minimum. And then at x equals 2, we've got y equals 7. And so that was our stationary inflection point. So that's the point 2, 7. And then at 2/3, we have our non-stationary inflection point right there. So it's changing from concave up to concave down at that point. And then at 2, it's changing from concave down back to concave up. So 2/3 was about -2.481. -2.481. We've got all those. All right, so you can see that, this, looking at f prime and f double prime and finding when they're zeros and using your sign charts, that gives you a lot of information about your graphs. So I've got a couple problems to practice. I don't want to overdo it. In section 18E, just numbers 4, F, and 8. And then in section 18F, 1, number 3, part G, and number 8 as well.